to everyone. Thank you for taking the time, middle of the summer, middle of the heat to attend this call. This is our regular bi-monthly DSATS community call. We have the regular update of the section, maybe 15, 20 minutes, something like that, not many slides. And then we have an interesting presentation by Isabel Witt. Is the same paper that she presented at the drilling conference in March. It was very interesting and well received. Paul suggested that we give an opportunity to rebroadcast, to reshare this information for more people to see. I think there is an application for automation. So before I jump the gun too much, let's go ahead and start with a regular update for the section. So this is our membership statistics from the end of June. So same trends that we have seen for the last year or so. You can see the green bars on the right side, how they compare with the 2022 numbers. So a healthy, I would say about 10% step forward, if you want, or increase, which is consistent with the rest of SPE and all other, most, I guess, technical sections. So no surprise there, but it's a good trend. On the lower right side, we see the student membership, which continues the healthy trend that we have seen, even though we know that we are facing some headwinds, with schools stop offering their programs, especially in Europe, and enrollment numbers in academia struggling. But it's good to see that there is some interest, from students. As we have discussed in the past, one of the opportunities maybe for us is to try to attract students from disciplines other than traditional, petroleum engineering or electrical, mechanical. And I'm thinking people like, IT, machine learning, operation research, other, let's say, fields that are more universal, more that can have an application in the energy sector. And as technology advances and changes and new energy domains come in, I think we can approach, those students. That's something that is an ever-present, topic. It is not going to go away from month to month. Anyway, so similar to that, distribution of the membership globally and across age numbers and different companies. These distributions don't change much either. The two biggest sections are Middle East and the Gulf Coast here. But there are some healthy numbers from other sections. And now, since March, we have, as DSATS, we have a bit better representation in all areas, in South America and Asia. So I think it's work in progress, but we can look forward to having some new members from those areas. On the company category, service always has been the most, the biggest group in DSATS, but there is some good numbers from operators, both independents and national companies. And the one we need to keep working with is contractors, working closely with IADC and ART, and that's also work in progress. Okay, so no need to spend too much time here. The next slide, I have an update, a one slide update for the work going on in DWIS. So as most of you are familiar with, we have 4 work streams there, working individuals, basically from the industry, working on a parallel approach, how to promote interoperability. In other words, plug and play capabilities for software or hardware that will enable efficiency and reduce costs and improve performance of automated drilling systems. And plug and play means, you have a software, an advisor or something from one company that you are able to seamlessly plug on someone else's rig and without breaking things, without having to spend, 2 weeks testing, commissioning, etc. So that's the general picture. The groups have been working on this for a couple of years now, and there has been some tangible progress individually, you know. So all this is coming together now, and there is a demo scheduled for September 19th at North. Eric and Benoit and the group over there are using the Open Lab simulator that they have, and on top of it, they're going to try to combine different modules from the different groups. There are 3 or 4 companies that have volunteered so far to build components. Halliburton, Secal, I'm not sure who else has an advisor. Of course, Norse has a big piece of the pie, building the platform. And the scenario that they're trying to simulate there is to using a well that comes from Aker BP. They provided the data, and they're going to re-drill virtually that well, where you, in the middle of drilling, you have all the pieces working together, you know, ROP optimization, etc., and you hit a stringer, a hard stringer. So now all the system has to adjust, change the priorities. For example, before you were trying to optimize the rate of penetration. Now you have different rules that come into play. And the idea for this demo is to see how all these pieces work together without breaking anything and without creating a havoc in the whole operation. How the data is passing back and forth between, and data that one advisor creates or produces can be consumed by another advisor without manually having to intervene and say, this is what channel A is, or these are the units. All this has to work, you know, automatically, so to speak. Of course, there are going to be more questions probably after the demo than before, but that's the whole idea, to start the discussion or to continue the discussion and bring up these questions that we need to ask and answer before we take this forward, you know, for deployment and case studies, etc. So I look forward to that demo personally, and I think it's going to be very interesting. Then with the advisory board, yes.
Yeah, sorry to interrupt you. Yeah. September the 19th is the IADC Drilling Engineering Committee Forum meeting. So it's going to clash with their quarter 3 meeting.
If we can move it. I don't see probably, I mean, there is nothing hard tied to this demo, you know. Yeah. I think there is some flexibility to move it.
Yeah, I think if we flag it, because it'd be a bit of a waste of resources if we do that.
Yeah. Thank you for catching this, John.
Okay.
So on the advisory board, the MAT has been holding regular bi-weekly meetings, and there is some very beautiful, productive discussions there. Without going down to the technical details as the work streams, looking to see how the value, what is the value of interoperability and what direction we need to follow there. So most of this is captured in the minutes that Matt is producing, but we thought that it's going to be excellent to have to create a position paper as the DWIS community with broad support, a wide range of contributors. And the idea there is to essentially make the business case for interoperability, not discuss the technical details, but why we're doing it. So an abstract was submitted. The deadline was extended, and we managed to meet that deadline. So that abstract was submitted, and now we're gonna work to put together a proper paper. And like I said, we're trying to have people from operators, contractors, service, independent contributors, consulting, academia, everyone that has been working on DWIS is welcome to participate and contribute. I think this is going to be a milestone for this effort to create more awareness and bring more people in. So that's what I had for DWIS. The next section is the drill botics competition that was completed last week. It's the end of the annual cycle. I think we have both Sasi and Fred here. Maybe, guys, you can take over here for a few minutes and give the latest update, the results.
Yeah, Fred, you want to go ahead?
Okay, we had our Group A contest and Group B contest, and the virtual rig winner was the University of Stavanger. They chose an option to drill using the Norse simulator and to detect and control a kick. And the physical rig was the Clausthal University of Technology, directional drilling through an actual rock. They've created their own RSS and were able to drill. They had some problems, but at least they were successful. But what we've decided to do is we're going to have the two teams join together and co-author a paper to present in Galveston next year. And that's a bit of a difference. What we're seeing is the work with DWIS, the work with Drillbotics, the work with DSATS. We're looking at the integration of applications with control systems. And what we see here is a first step for Drillbotics, and to push that forward in the future to try to continue to build on that. We've been given a booth by SPIDC. And then there's always Fred calling for money. Because we got two teams co-authoring, we've got twice as many students that we have to fly across an ocean. So we need some sponsors. And we got to have at least $5,000 for that second team. And if everybody on this call could contact their boss and say, can I donate $500 to Drillbotics? We'd be in good shape. And so do what you can, ask for some money. It would really make a big difference, because we'd like the whole team. We don't want to have to limit to the teams going to Galveston to only maybe 2 people or something like that. So it all depends on you guys. And then I need one more volunteer to give us $500 for the university in Ghana, UMAT. They have to buy their own internet connection. They have all kinds of stuff that they do because the schools can't afford it. And all we need is about $500. So somebody who has a tie-in with Ghana, it'd be an absolutely great place for you to contribute. Thank you.
Thank you, Fred.
Dimitrios, just one last comment.
Yeah.
We are kicking off the planning for 2024 competition. We have scheduled a meeting next week, so anybody on the call, if you're interested, please reach out to any of the 3 people on the slide here, Fred, Enrique, or myself, and we'll add you to the meeting invitation.
This is for judges, Sasi, right?
Judges and our contributors, volunteers who want to help us
okay.
for next year's competition.
Excellent. These slides will be available on the website, so if you don't catch the emails, no worries, you can always get them later, or a screenshot now. All right, so let's move on.
One question about sponsorships. We tried to do something about 1.5 years ago, and that was a spectacular failure because SPE required to complete sponsorship contracts from Noble, in which if we can just provide credit card details, that would be much more simple. So, Fred, how are we going to get the money to you if we decide a positive thing?
That's fixed. I would like to think now, Robert, because with the new website that we have, we can accept payments, credit card payments directly to DSATS without having to have, SP in the middle, contracts and long-term agreements and commercial rights, etc. So as long as you have internal agreement to sponsor, you can go make the payment and just let us know how you want that money to earmark it, basically, and tell us this is for Drillbotics, and that's it, really.
Okay, so that's very positive to hear that. And if I may suggest to Fred and you is send out an email with that message. Hey, we need money for X, Y, Z. And this is the way how you can do it. And then make it super easy for people to actually initiate that. Because I know that more people are running into the paperwork barrier. And but if that is fixed, then I think send an email blast out and say, hey, this is how you do it, and donations are welcome.
Okay, very good.
Will do.
Action for us, Fred. Okay, thank you, Robert. So moving to the next topic, this is an initiative that is not yet a formal activity. We discussed this in the last call as well. The top level view is that there is enough interest on the technical side to make sure that any developments, technical developments we do on drilling systems automation, we don't ignore the human factors aspects, how the technology, how the applications will interact with people, and how do we make sure that there is always situational awareness, that the workflow is smooth, that we don't disrupt, the current processes, that we don't overload the people, etc., etc., etc. So this has been in the forefront of the discussion for years, but nothing really formal, no activity formal to look into this problem or into this challenge. And we have tried different avenues how to produce something material for this, how to work with people that already are working on this, ergonomic societies, human factors. Every individual company has something along those lines, but there is nothing coordinated, So the latest effort is that we're going to work closely with IADC and the ART group and try to push this forward under the IADC umbrella. Why? Because the contractors will be a key factor in this effort. And that's where it stands, essentially. Shashi, feel free to give the latest here. I'm just maybe carried myself away.
I think, yeah, you covered it right. The big action, and in fact, I'm trying to schedule a call with my counterparts on the IADC art side for next week to define a set of deliverables for the proposal so we can go back to IADC art and then present it to the IADC board.
So that's where what the current status is. There is support within the art group. Both Blaine and Sarah are supportive, but they ask that we have a clear set of objectives and deliverables for this effort before we present it to the IADC higher up for approval. It's important to get the contractors on board and get them to buy into this effort. That's why we're going through this pain. It's slow moving, but it's moving. That's the important thing. I don't know if you want to add something else, Shashi, or if any of the people in the call are interested to know more, Shashi is the contact for this initiative. All right. Next topic is the list of events that we have coming up. Events means SPE lives, webinars, and there is the ATC reception. I have a separate slide for that. I think Austin is here also to give some more details. So these are the dates that we have been assigned by SPE. We have an SPE live at the end of August, and it's open. We don't have right now a topic for that session. We do have a topic for the next webinar, September 21st. Serafima with Exebenus in Norway. She gave a presentation this year in a workshop that was held in Kuala Lumpur in automation. And she kindly offered to give that presentation again in this webinar for the broader community, DSATS community and others, So that's the topic over there. I think it's going to be an interesting discussion. Everybody's talking about AI these days. So let's see what Serafima has to say and how this has been used and applied in our field. And we have one more webinar for November, which is also open. And if anyone here in the group has something that they would like to share, to show, a success story or any development, please get in touch and we can try to fill those two spots. So on the reception itself.
Demetrios, quickly here. I wondered on the August the 30th, is this an opportunity? It's a 30-minute SPE live that goes across SPE. I wonder if it's an opportunity for Drillbotics with Fred and Sashi to be interviewed by somebody and talk about what Drillbotics is doing. It would get it to a wider audience than just the automation folks.
Okay. I think it's an option for sure, yeah.
Just leave that on the table for consideration.
Yeah. Okay, thank you, John. Let's keep that on the table. Yeah, absolutely. So for the reception in October, so I think Austin is here.
Yes, can you hear me okay?
Yes, Austin, please go ahead. I have the slide on.
Okay, thank you. Yeah, so very much looking forward to this networking event. For those of you that haven't heard or weren't a part of the last call, basically the format is going to be small discussion groups led by various industry experts. So far we have 12 identified candidates that have approved to be one of our experts. I think we have very good representation. We've got people from, Schlumberger, Baker, Halliburton, Borva, Neighbors, H&P, Precision, some representation from academia, and then of course a few operators as well. So very excited about the list of individuals who have agreed to be our industry experts. Over the next couple of weeks, hopefully we'll start a marketing campaign where, each of these individuals will be, posting about the event and, trying to gather some interest in attendance. But it will be a really good opportunity for some of our younger members that becoming more involved in automation or AI, geothermal, to meet some people that are, leading in these spaces. So the general format, we'll have about, 12, maybe 14 spaces where individuals can congregate, with one of these, one of these industry leaders. And it'll be open where people can move from, one topic to the next. And the $25 entry fee will include 2 drink tickets. So it should be a fun event and, an opportunity to, like I said, to network with peers and also these experts. The main topics that, we're hoping that this networking event will be around is, as I mentioned, the kind of the future of automation and geothermal wells, leveraging machine learning and AI, and then also, an important topic around how do we manage liability and risk, particularly when we're talking about these integrated automation systems. If say a contractor is doing the automation, but the service provider's app is running on that contractor's rig, how do you handle those problems from a liability perspective? So very excited about the event. The time will be on Monday from the first day of the conference from 5 to 6. So we're hoping we get a good crowd right after the main agenda or presentations throughout the day, but before maybe people's dinner plans. So the link to register for the event is already up. So hopefully everybody on this call will get a chance to attend. And like I said, it's $25. The link is up. And I hope everyone's able to come out and take advantage of this opportunity. Like Fred, we also need money. I'll be looking for corporate sponsors over the next couple weeks as well. So that's all I had in terms of update. Wanted to see if anybody had any questions.
Thank you, Austin. Any questions? Yeah, I mean, the registration is open, like Austin said. I checked it yesterday, I registered myself. So yeah, I mean, no reason to wait for the marketing campaign to launch. If that sounds like a interesting, fun thing to do, you know, it's in between the day's program and dinner. It's a good session to go meet some people, have a chat and talk and before dinner. So that's it on this update.
Yeah, Demetrius, I think it's going to be a great event. I think Austin's landed on something very interesting here. And the IADC in the Far East, they held a young person's event like this, and they were reporting it was very successful. So I think that the format should work out very nicely.
I was checking all the special sessions and dinners, etc. And everything is $80, $100, and ours is $25. And I think that will open it up for broad participation.
Yeah, should do.
All right, very good. So I think we are now, that's it for the regular update. Then we are at the point where Isabel can take over and go through the technical presentation. I'm going to stop sharing here. Isabel, can you try to bring up your slides, please?
Yep, I'm just trying right now. Give me 2 seconds.
There you go.
Can you all see my screen?
Yes.
All right, fantastic. Good morning, everyone. Thank you for making the time. Apologies in advance to anyone who already saw this in Norway. You can just tune out for the next 20 minutes and then throw some questions at me at the end. But essentially what I'm presenting today is the paper that we presented in Norway earlier this year in March. And all this paper was saying how we could use downhole data, combine it with some solid engineering, a little bit of physics, and come up with some really good recommendations to improve drilling performance. After we completed this study, I know Exxon has been working on some ways to improve their auto driller systems. Pablo, who is my co-author on this paper, he's dialed into this call. So if you have any questions after about what they're doing and how they're using this data, Pablo will be able to help answer those questions. But essentially, what we're going to talk about is an introduction. So, you know, what were we doing, what the application was, and the observations we got from doing this data analytics work, followed by the results and the conclusions. So essentially what we did, it was I think we did 9 runs in this application for XTO, and essentially we ran a downhole sensor inside the drill bit, and this sensor itself can not only measure vibration, but downhole torque, downhole bending, and downhole weight. And the goal of this study was to make sure we could work out what was going on downhole and how we could engineer those problems away. The data itself is recorded in 1024, so you've got 1,000 data points per second, so really, really high resolution, which is really fantastic. So you can get a really good idea. We can see the HFTO, we can see the lateral vibration, we can see the stick slip, we can see everything. And so usually we take the 1024 data, we downsample it to 1 second, have a look what's going on in the 1 second space. And if anything doesn't look right, then we'll go back into the high frequency and look at it. So essentially we took this data at the bit to try and work out what the dysfunction was, and then we tried to engineer it away. So the background, so what was the problem and where were we drilling and what were we trying to solve? But essentially this was an 8 3/4 lateral production hole. On the far right, you can see a trajectory, just a stylized trajectory of the well. And you can see we're going down close to 17,000 foot TVD, and then we're going out another 10K. So we're talking about measured depths of 25, 27,000 foot. So really, really out there. And the target zone was this really, really thick, hard, abrasive shale with interbedded chert, as well as pyrite. And so if anyone who's involved in bit forensics or drill bit damage, you'll know that chert and pyrite are not friends of PDCs. They will destroy cutters very quickly. And in terms of this actual shale, and I use the term loosely, it was, like I said, very abrasive, very high quartz content. So we were getting a lot of premature PDC failure because we were destroying the cutters in the chert and the pyrite. We're destroying the shoulder cutters in this abrasive shale. And so we were really having troubles with the run lengths. I think on average, some of the wells were doing 200, 300 foot runs, and then we were having to come out of the hole to change BHAs. And so when you're really out there at sort of almost, 25,000 foot, to do a round trip, that's a lot of tripping time. So can we improve this runtime? What's going on from a dysfunction standpoint? Can we mitigate that, and can we improve the run life? And we did improve the run life. And so, like we can see here, was taking close to 35 BHAs to complete this lateral. So anything was an improvement from 35, and that's what we were trying to achieve. Going back to this dull condition, this is a typical dull condition from the application. So you can see, there was a lot of thermal damage. You can see the thermal degradation of the diamond table, a lot of chipping, a little bit of tangential fractures. You can see these tangential fractures. And so, it doesn't look like a lot of damage, but when you're in these really, really hard shales that are close to, you've got these 35,000 PSI rock, it really is not your friend. And so as soon as we were getting a little bit of dulling of these cutters, we were struggling to continue to drill. And so the goal was, how can we improve this dull condition? So what did we find out during the study, and how did we use this data to improve the run life? First one, really poor weight transfer due to drill string buckling. So that was the first thing. We had a hypothesis that it was happening, but we were able to prove it with the data. The second thing was tearing issues surrounding weight on bit and differential pressure. So this is something we see all the time now that we have these downhole sensors where we can measure downhole weight, downhole torque, and we can see that, hey, on surface, we only thought we had 30, but downhole, we actually had 40 because we've teared incorrectly or something like that. So we see this one all the time, not only in this application, but once you have eyes downhole, it really does help understand why you're seeing some of the damage you see. And the third one was the loss of ROP due to whirl as the tool joints pass through the rotating heads. So all this work was done with rotating heads. And obviously, when you try and push that tool joint through an RCD, you have that momentary drop in downhole weight. And we can see that with the sensor. But what is interesting is when that weight comes back, how that bit and BHA reacts to that, and how we can enter into this dysfunction state. So poor weight transfer due to drill string buckling. So on the left here, we've just got a sort of a chart with a lot of words in it. So essentially surface weight, downhole weight, and then this line through the middle. In an ideal world, this is where we'd have perfect weight transfer, right? Obviously, if you're on this half of the chart, where you've got higher surface weight and lower downhole weight, if you're sliding, you'd expect your data to be here. If you're hanging up, you'd expect your data to be here. If you're buckling, your data is going to be on this side. On this side, really, to get here, you need to be zeroing with load on your bit or something like that, right? So you think you've got 100, 100 or 30,000 pounds surface weight or something like that. But then downhole, you've got, close to 40,000. So that means you've essentially zeroed with 10,000 on the bit. So it's really, really interesting when you have that downhole weight and you create these cross plots and you see where your data lies on that cross plot, what is going on. So in this case, you can see on the right here, this was one of the first runs we did. The data is colored for stick slip indicator, just to have an eye what's going on from terms of stick slip, nothing really bad. But essentially what we were noticing, if you look at surface weight on the x-axis and downhole weight on the y-axis, is none of our data is falling on that perfect weight transfer. Again, because we're in a really extended lateral, you expect there to be some issues with weight transfer. But what was most noticeable is after 30,000 on surface, if we keep going in this direction to the right, you can see you're going 30, 40, but if you look at the downhole perspective, after 30, I'm putting this extra surface weight and I'm getting no change downhole. So to us, that really indicated there were some issues possibly with buckling. And then we investigated some ways to fix this. And so our friends at Exxon, they ran some slack off rotating tension analysis for this, this well one, run one. And so you can see this is the trajectory of this actual run. So you can see it's not to scale. but it's a little bit higgledy-piggledy. But essentially, what we've got here is we've got the tension on the x-axis and depth on the y-axis, and the red line is the helical buckling limit for this run. And then the green is the BHA. And so all we really need to take from this graph is when that red line is above that green line, that indicates it's possible that we have some sort of severe helical buckling. So what we thought was, hey, well, how can we mitigate this buckling through this region here? And so if you look at the graph on the right, that buckling was happening in this yellow zone here. So that corresponds with here. So what we said was, hey, let's just run some heavy weight through that section where we're getting the buckling, and let's see if we can actually change, if we can mitigate that buckling and increase that critical buckling load by just running that stauncher drill pipe through that section there. And so we did that. And then we looked at the results. So there were a few steps we had to go through before we got there. So this was the data I showed you guys originally. And so this was the first run in that well. And like I said, we had that buckling. And this was a motor-assisted rotary steerable. We had the great idea for our second run in that application. Let's just run a rotary steerable without a motor and just see what happens, right? Maybe if I increase my surface RPM, because obviously once you have that, just a plain rotary steerable, you got to up your surface RPM because you need to get some of that rotation downhole. Let's see if we can actually get rid of the motor, reduce the actual revolutions being done by the bit. Maybe this will reduce some of the wear we're seeing on the cutting structure. That was obviously not the case. We got ourselves into a situation of severe stick slip. So you can see our indicator is from 0 to 200, and you can see we were essentially in severe stick slip because of that loss of rotation at the actual drill bit. So that was not the solution. But interestingly, with that increased surface RPM, we seem to have been able to shift sort of that point at which we were seeing that buckling, and at the point at which we're just getting better weight transfer a little bit. But by the third run, we went back to the motor-assisted rotary steerable. We said, yes, that's the way to go, and let's put that heavyweight drill pipe in that section that I said before. And once we had that heavyweight drill pipe in there and we ran it through that region where we thought the buckling was happening, you can see how all that data has shifted from down here into this section here. What we did notice specifically for this run was now we actually had a lot of data up here, which is problematic because this is telling us that we've teared incorrectly on surface. So we've somehow put more weight on the bit than we thought we were putting. So that in itself is another problem that I'm going to discuss in the next coming slides. But if we just focus on how we've been able to shift the data from here to here by improving that buckling, that was a real win for us in this application. And that was sort of proving that idea that, yes, we did have buckling through that region. And yes, with that stauncher drill pipe, we were able to increase that critical buckling load. So this data here, what is going on? I've got 20,000 on surface, but downhole, I've got close to 40,000. What have we done here and why is this happening? So essentially, we were drilling along. We've got, just to explain what's going on here, we've got two stands of data. This is time-based data. You can see I've got one stand here, one stand here. This is block position. And as we're drilling along, originally, our surface weight and downhole weight, we're having really good weight transfer. We're really having a great time. Everything is going well. We're high-fiving ourselves. And then suddenly we drop the GPM from 500 to 450, right? No problem. These things happen. We had a bit of losses. We had to drop the flow rate. What we do see when we drop that flow rate is that immediate shift between downhole, which is the red, and surface, which is the blue. At the same time, we have an immediate surface torque and ROP response. I just realized I don't have the legends on here, so I'm really sorry. But essentially, the blue here is surface torque and the green is ROP. And so you can see as soon as we have that increase in downhole weight, we're getting an immediate ROP and torque response. So instead of thinking that this might actually be a sensor issue, we can see that it's actually really happening, that weight's happening, and that weight is going to the bit. And why is that happening? What has happened here? So essentially, the fluid shear along the outside of the pipe causes hydraulic lift, and with it a little pipe compression. So if you think about, you know, that fluid moving past the pipe, that actually causes a certain element of pipe compression. This becomes more pronounced the smaller that restriction is between your wellbore and your drill collars. I mean your connections on your drill pipe, where you have that increased external upset. So essentially, you've got that fluid shear happening on the pipe, you've got the pipe compression, and what happens is when you change that flow rate, it changes that pipe compression. So essentially, that hook load tear value should have been re-zeroed. The hook load should have been re-zeroed, because once I drop that flow rate, that actual physical hook load that we are carrying is changing. And so that hook load was not retailed after that change in flow rate. And as a result, the auto driller thinks, hey, you know, my hook load is increasing. I've put more weight on the bit, right? Because it goes, oh, my hook load is increasing. I need to, you know, back off a little bit here. And so what ends up happening is it ends up putting more weight down hole. And then you got indicated on surface, it thinks it's okay because it's adjusting itself on surface. And so the end result was we essentially had a delta of 15,000 pounds between the downhole and the surface weight, which is really not great. The result of this means we put too much weight on this drill bit in this application. The amusing thing about this was we had more than one sensor in the hole. So we had our downhole sensor, and then they had their separate contractor had another sensor in the string. And when they were doing their analysis, they actually just said, oh, that's really weird. And then they matched the two curves together. But if you look at what's happening in terms of the operations and how those hook loads are changing and how the auto driller is responding to that, it is an actual real change. We've ended up putting too much weight on the bit. The end result is our data ends up here. And so you can see when we went from that higher flow rate, we started to drop that flow rate, and then we had that reduction in pipe compression and that increase in downhole hook load. You can see it's all happened when we've dropped that flow rate, right? So when we've had that hydraulic lift effect change. And the end result was we actually started to break that inside cutter here in the cone, right? So those cone cutters take the most load, and the more weight you put on the cone cutters, not so great. Because they do take the most load on the drill bit, and you can fail them. And especially in this application when the formation is so hard, it resulted in a situation where that increased sort of 16,000 pounds ended up with us damaging that cutter. Oops. I don't know how we ended up there. So yeah, that was the second thing we noticed. So the third thing we noticed was the ROP loss and the initiation of whirl as soon as that tool joint passed through the rotating control device. And so you can see really clearly here, again, similarly, we've got a standard drilling, and you can see we've got these tool joints. And so the surface weight is the blue here, diff pressure is the green. And you can see very clearly that when we come through the rotating heads, we're losing some of that surface weight. It's hanging up, and then we're losing some weight there. And so the end result is it hangs up, it pops through, that surface weight goes down momentarily, and it comes back. And you can see when that surface weight pops, when it comes through, and we lose a little bit of weight and it comes back, you can see this lateral vibration is increasing from 10 Gs to a sustained sort of 15 to 20 Gs. You can see also when it starts to hang up, we have that decrease in diff pressure. So that does also indicate. And then once it pops through, you can see it sort of pops back up again. And so the problem is this, is when you have that loss of depth of cut, right? So you're hanging up and you're losing your downhole weight at this point. When you start to get that weight back, you don't have that supporting axial load through the bit and the BHA, right? And you have that friction acting on the outside of the drill bit. And so when you have that external friction without that sort of stabilizing axial force through the center of the BHA, it wants to rotate off center. And due to hysteresis, the only thing that's really going to stop this lateral vibration is picking up off bottom and recycling your pumps, right? Or making a connection or something like that. So in this case, in both cases, you can see we've tagged that RCD, you know, we've lost, in this case, diff pressure downhole, we've popped through, but you can see that vibration starts and continues to the end of that stand where I make a connection. Same thing happens, I start drilling on the next stand, we keep going, and suddenly we hang up in the RCD, we pop through, we recover, but when we recover, that lateral vibration and that off-center rotation is going out of control. In this case, it led to the premature failure of this run, this severe lateral vibration. You can see here we start to pick up and come out of the hole. And essentially, when we look at this dull and we see what's happening on surface, you can see how we've again destroyed the cone of the bit. You can see there's some side loading here, which is a little bit hard to see in this picture, but you get, when you have that off-center rotation and you have that little core in the center and it's a hard core, you get the back and forth scrubbing of that drill bit. And what happens is you will see damage to the cone of the bit. At the same time, you know, obviously lateral vibrations will damage the outside of your cutters here as it goes back and forth and interacts with the well bore on the side there, especially in that hard formation. So what we were seeing was just if we sit there and we hang up and we lose that downhole depth of cut, we get ourselves in a really bad situation. So how do we fix this and what can we do? And I know a lot of companies have been looking at this sort of stuff, but the goal is to maintain that constant depth of cut, right? You don't want to lose that engagement of the bit and the formation, because like I showed, when you lose that depth of cut and then as you re-engage, that friction on the outside of the drill bit pushes it, you know, and makes it want to rotate off center, and it changes the center of that rotation as it interacts with the borehole. And so the goal is, okay, so can we maintain a constant depth of cut downhole, and how do we do that? And so essentially what we thought about doing was finding out what is the surface weight we need to actually push that tool joint through the rotating head effectively without losing weight downhole. And so what this meant was, what we would do is we would engage ROP control, just a couple, we'd look at the ROP just before we're hitting that, that tool joint's going through the RCD, and we would set that as our ROP control point. And so as a result, if I'm in ROP control, my auto driller is going to continually try and increase the weight to maintain that ROP control until obviously it pushes through. At the same time, you need to have your surface limit on your auto driller set, your surface weight limit set to a value that's going to allow it to maintain effectively, you know, this constant ROP and that constant feed of line off the drum. And so in this case, it was 15,000 pounds. And you can see in these cases, you've got 3 tool joints here on this stand. We're setting an ROP control. And as we set an ROP control, instead of that weight actually dipping down here and coming back, it's staying relatively constant. If not, we're getting a little bit higher downhole weight on bit, right? This one seems to have worked really well. They've set it, you know, at a good point, and it's been able to maintain it more flat. Obviously, you know, a lot of this involves manual changing, manual observation, all that sort of stuff. So it's not exactly, you know, a perfect science, so to speak. And Pablo will be able to talk a bit more about what they're doing internally now with their recontractors to try and automate this type of stuff to ensure it doesn't happen, so we can maintain that constant weight and bit downhole. But, you know, it's honestly, you know, we don't see it on every single connection. We do see it on some. Obviously, vibration is not a big deal. If you're in a softer formation, you're not going to see the same damage. But when you're in these harder formations, any type of dysfunction is going to lead you into a point where it's just not so great for the condition of your drill bit at the end there. So just in terms of what this looks like in the data, and this is just a little reminder for anyone who does look at downhole data on a regular basis. I'm not quite sure how many people on this call do, but essentially, you know, when you do introduce something like this, where you're increasing that surface weight to pop that tool joint through to maintain that constant downhole depth of cut, you introduce a new artifact into your data. So you can see here, we've got 2 stands of drilling, and these little tool joint states show the points at where I'm pushing a tool joint through the RCD. And what we have here particularly is that surface weight is increasing. But if you take this data and you create a downhole surface weight cross plot, you can see when I introduce that surface weight, I actually introduce an artifact, right? So I actually have a bunch of data now sitting on this side of the chart, which is telling me, you know, if I was to look at this data in a vacuum without understanding what's going on here, I would think, oh, like I've got some crappy weight transfer. But it's just good to remember when you do stuff like this and you make these cross plots, you need to understand what is happening in your surface systems, what have you introduced, because this will affect your data quality. So this is something I talk about a lot. So yeah, just keep that in mind when you're looking at cross plots and understanding different relationships. You might have introduced the problem and it might not actually be happening. So what were the results? I know I've just spoken about a lot of different things and gone back and forth, but these were the actual results. So what we have on the y-axis is duration in minutes. The column chart back here, it's colored for the amount of time I spent for that stand in lateral vibration above 6 Gs. And the amount of time I spent in a stick slip state above 75%. And so these are the same runs I showed you on the cross plots at the start. So we've got the first run was the motor assisted rotary steerable, the second was the rotary steerable, and the last one was the motor assisted rotary steerable with the heavy weight in the buckling zone. So on that first run, you can see when I had that poor weight transfer, the blue here is my downhole weight. And you can see when I have that poor weight transfer, and as I damage my bit, you can see that lateral vibration is increasing. You can see that downhole weight is sort of hovering between, I think, like sort of 20 and 30. The second run, I'm not even going to spend much time on. Obviously, that stick slip was out of control. It was just a total disaster. But hey, we tried something different. And, you know, if you do the same thing over and over again, you're never going to get a different result. So we tried something different, did not work. Third run, we learned our lesson. So we went back to the motor assisted rotary steerable, but we put that heavy weight in the buckling zone, right? And when we put that heavy weight in the buckling zone and we improved that weight transfer, you can see my downhole weight is now in those 30s to 40s. What I've also done by improving that downhole weight, I've also improved my engagement of my bit with my formation, right? I have better depth of cut. You can see my ROPs are much higher. You can see how my ROP went down here as my lateral vibration increased, as my bit degraded. Whereas in this case, I had more weight, more ROP, less vibration. So by identifying the buckling, engineering the buckling out, as well as making a couple changes to how we operated in terms of making sure we teared correctly, making sure that we implemented this system in terms of pushing the tool joints through the RCD to make sure we maintained that constant downhole depth of cut so we didn't go into like a vibration state. We've managed to mitigate the majority of the vibration we saw, and we've managed to improve performance. And so this chart here on the right shows the change in performance we've had across the well. And the conclusion really is not that we didn't run these sensors and suddenly everything was solved, right? And the sensors provided all the solutions. The sensors don't do any of that. All the sensor does is collect data. And then we can use that data to support our engineering hypotheses. We can use it to support our decision making. So in this case, in general, you know, running heavyweight drill pipe through a buckling zone is just not a practical thing moving forward. But what they'd wanted to do for a long time was to replace the 5.5-inch drill pipe with 5 7/8, right? Bigger, stauncher drill pipe. Critical buckling loads are increasing. It's better for torsional dysfunction as well. And so the data gave us the permission, so to speak, to be able to justify changing a drill string, right? Because buying an entire new drill string is not cheap. Changing all your handling equipment is not cheap. It's not something you do lightly, but the data supported it. So we did it. There were also some other engineering changes we did. There were some changes to the well trajectory as well, just to improve its, you know, tendency to want to buckle. And then, like I said, there were more stringent operating procedures to address those things that we were getting with the crappy tearing, that tool joint dysfunction. And so really communicating clearly with the field personnel, when we do this, this is what's happening and this is the result. So we have to be really stringent on when we re-zero, when we, you know, understanding the situations and when you need to re-zero. And the end result essentially was a really, really, really good improvement over the run life. So when we started this, and that data that I was showing you from, you know, run 1, 2, and 3 in that well 1, the average run length was 217 feet. So really, if you're drilling in triples, that's only a handful of stands before having to trip out. Obviously, when you get to the end here, by the 4th well, and obviously we had the larger drill pipe at that section as well, you can see we improved performance by 270%. So really, 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 really good short-term gains. Pablo, I'm not quite sure if he's still on the call, but he'll be able to fill us in with where they are now. I know they've set some real record wells in this region compared to when they first started, and we were in that sort of scenario. So thanks for your time. Hopefully that was interesting. Sorry if you'd already heard it. Yeah, if you have any questions, just let me know and I'd be happy to answer them.
Is Pablo on the call, or we can open it up for questions?
Yeah.
Go ahead, Pablo. Any comments?
Yeah. Yeah, no, this is Paul. I'm sitting here. I'm in Argentina right now. We're getting ready to drill 2 wells, and you know, this kind of a breakthrough on how we look at rig control systems. We're presenting a paper at the ATC with the rest of the story. I mean, there is approximately another 12 months worth of work with 4 drilling rigs that was initiated by the work done led by Isabel and Paul Pastusek. And the interesting thing is that, you know, every well, the run length kept getting better and better. So if you look back in the late 2021, in the most difficult basin that we have right now, it's taking up to 64 BHAs to drill some of these wells. And we just took those rigs. They're going to carbon capture, but we our last pad, we had back-to-back 4 BHA runs in those wells. So very good engagement on driller procedure. We actually, the name of the paper we're publishing is The Role of the Auto Driller, Rig Control Systems, and Driller Procedures in reducing BHA failures. And our approach right now is challenge the rig contractors to provide unconditionally stable rig control systems. Some of them are doing it through procedures with the drillers, heavily focused on ROP mode tests. You know, you go into this function, then you switch to ROP. But then some of the rig contractors that we have are actually working on automating some of the responses required to mitigate dysfunction that we already know is going to happen, right? The curve bit is too aggressive and you're going to have a slight dysfunction. So we already have the scenario that the rig system is going to read. So there's been a lot of momentum from our 2 big rig contractors. They continue to put effort and resources into surveillance of rig control systems. And we have been providing high resolution data from our directional tools. And it's been really interesting to see how the top drive high resolution data is coupled with the RSS vibration data. And that has kind of provided some insight on what they need to do from a tuning perspective. So that continues to progress really well. And obviously some of this new technology of being able to get downhole sensor data processed.
We lost you, Pablo.
Can be turned around in 24 hours, but she was making it happen. And right now, what we're focusing on from our data science standpoint is we're developing an auto driller health model that will kind of alert our rig supervisors when there is dysfunction. Our conventional practices for mitigating whirl and stick slip, but while we wait on some of those other upgrades for rig control systems, we're also using some of this technology to measure effectiveness of anti-stall tools, you know, investigate dulls, and it is really a new avenue for us that from a drilling mechanics standpoint. So we're going to trial our model, auto driller health model, in the upcoming 2 Argentina wells to fine tune it. Right now, I think we're dysfunction versus what the model considers dysfunction. So we're kind of fine tuning it. And like I said, we're going to be presenting a study on 4 rigs and 350 BHA runs in October. So thank you, Isabel.
Thank you to both of you guys. Thank you, Isabel. Thank you. If I can just offer a couple of comments, I think it was an excellent presentation, and it covers a lot of new, let's say, way of using high frequency data to analyze the mode of the operations, what's happening, etc. So, coming a little bit from an automation point of view, what does that, all this new information, very useful information, how does that help us from automation and interoperability and the stuff that we're doing mostly on DSATS? I think there is a lot of overlapping, a lot of lessons learned here. For example, the first one, you cannot trust the data blindly, what the sensor is telling you, whether it's the surface weight or we saw the difference that Isabel showed us. You have 20,000, you think you have 20,000 and you have 40. That's something that is not the fault of the auto driller. It's not the fault of the automation. It's what data we feed it in. So data quality, like we have been saying forever, many people, is very important. And it's not a faulty sensor here. Is how you calibrate it. It's how you do the tarring. Maybe you can use modeling to correct the physical measurement, to derive a calculated measurement downfall. So there is a lot of gaps, a lot of pieces that are needed to make automation work at the end. So I'm saying this, and maybe I'm on a soapbox here, but let me just carry my thought. People draw conclusions whether automation works or doesn't work without dissecting and getting to the bottom of what happened. This is something that we have really to pay attention to the details before we make this kind of decisions. And this is an excellent paper, in my view, because it points out of what can go wrong and where the responsibility lies, where the fault lies, and make the right conclusions. Yeah, sorry, I'm going to stop here. Someone else has a comment?
No, I think this is Pablo again. I think that we're still struggling with identification of breakover, of hook load, and that continues to be dependent on the person, right? On even the understanding of what breakover is, and that's something that I don't hear a lot. This is how we're identify that this is proper breakover. And we've been bringing it up for the last 3 years, but there's really, I guess, a lack of understanding or a lack of seeing the value of the importance. So unfortunately, that's still that is something that we're still trying to figure out how to control it or alert. Stand by stand, hey, this is a good breakover, this is not.
Something else that I think pops out of this presentation that is more related to the DWIS world. We saw when the flow, the GPM, went from 500 to 450, that the change that is caused in the measurements, and that the ideal way to address that would be to recalibrate the weight on bit, and so you have a better measurement. Now, that sequence of operations, what does that suggest is that the optimal flow, depending on the value of that optimal flow, the sequence of actions changes. If you had stayed, for example, at 500 GPM and everything was fine, you stay on bottom, you drill. Now that the optimal flow coming from somewhere, from an advisor or a person or whatever, it's not 500 anymore, it's 450. Now that creates a new sequence where you need to pull off bottom, calibrate, and go back down. And what automation system, what sequencer is smart enough today to do that? Now, of course, that is now competitive market advantage, competitive advantage. The sequencer of one company is smarter, let's say, than the sequencer of the next company. The important point is to capture that intelligence. Also, not just offer the framework for information to go back and forth, but capture the change in the activities that need to happen. That is key part to make the whole system successful. Otherwise, if we keep drilling with 450 and we have the wrong measurement, it's not the fault of the automation what's happening, is that we don't understand what's going on. So it opens, I think this presentation opens a lot of questions of, assigning value where it belongs and focusing on what we need to do, the interface, the intelligence, the data calibration, the sensors, etc. So I think it's an overall excellent presentation, even though it's not directly on automation. And I would like others to chip in, and offer their views, their comments, what ideas that triggered as you went through this presentation.
Yeah. So Demetrios, one comment from my side. I think what's interesting is, evaluating competing or contradicting KPI targets. So, for instance, everybody recognizes the importance of getting a good tear, a good zero on your weight on bit or differential pressure. But for instance, as you get deeper in the lateral and you turn your pumps on, you need more stabilization time, as an example, before you zero your weight and differential pressure. Well, to do that, you have to sit off bottom for a longer period of time before going to bottom. So that directly competes with maybe your flip to weight target. It also has other implications, like if you're sitting off bottom, rotating at a high RPM before you tag bottom, you might be introducing some type of other vibration. So I guess what's interesting is, or I think a thoughtful thing to add to this is, whenever we introduce a new technology we want to use or a new procedure, to reevaluate all the potential competing KPIs, so the directive to the field execution team is not conflicting.
Yeah, very good. Thank you, Austin. John, please go ahead.
Yeah, this is for Isabel. So on your hydraulic lift there, did you so these are weight and bit sensors, and as Pedro just illustrated, these are high gain sensors with detecting a very small change in the stress state in the BHA and amplifying it considerably to get a measurement of weight on bit. And when you change the flow rate, you also change the hoop stress in the pipe. So the question is quickly, you've identified this as being due to hydraulic lift effects, right? So your surface weight differed considerably from the downhole weight. But did you also investigate whether, in fact, the downhole gauge was affected by the change in flow rate because it wasn't compensated correctly? So the tear conditions changed, basically,
100%. And as soon as you change the hydrostatic conditions downhole, it will affect your strain measurement, right? And so initially that was a problem, and I've just gone back to the slide here because you're mid-stand here, and obviously every time when we look at downhole data, we will actually physically pick that tear point at the start of the stand, right? So you can see the point where you have that inflection in torque and inflection of weight after that.
Are you sharing something? Are you sharing something as well? I don't see it.
Yeah. Sorry, I stopped sharing my screen before just to stop distracting everyone. But so like I said, with the hydrostatic changing, that will affect the measurements by the strain gauge, right? So at the start of the stands, when we do this type of work, we will re-zero at the start of the stand. So we'll look at that inflection point. We try and find, like, I think, was it Aaron who just said that we have to wait a long time for that pressure to stabilize. So we're not always in that perfect scenario where we have fully stabilized pressure before we zero and what we call zero for that tear point. And so it is really hard mid-stand like this. You have to manually take into account that what that change in hydrostatic from that change in flow rate is and what that effect on strain is. But what most notably in this example is we make the connection and we go back to bottom, and this was a very clean tear point at this stage. So to us, it was very clear that this was definitely weight that was happening downhole. But yes, 100%, we do take into account that change in hydrostatic and the effect on the strain gauges. It's a little bit hard because you have to sort of understand what's going on, but it got done and it was done. And yes, you are right.
Okay, yeah, it's just a comment because having worked with these, I mean, you have to really measure the differential pressure to get the hoop strain and stuff like that, and then the temperature effects are tremendous as well. I mean, we were using a weight bit gauge to monitor whether our high bay door was open or closed, yeah, and we could detect it just by a minute change in temperature, a fraction of a degree. So as soon as you change the flow rate, you change all these things, and unless you measure them, then there's a chance of error. Okay.
Okay. And we're at the stage now with this technology where we're doing some work where we're trying to automate the tearing, and we're trying to take into account those hydrostatic and hydrodynamic changes and doing calibrations on those sensors before they go in the hole. So we can actually, instead of having to manually do this and manually look at it, it's got to automatically understand that when you have this, change in pressure, it's going to be this change in strain and so on and so forth. So yeah, we're doing lots of work internally on that to automate it as well from our end.
Okay, good. And also on the distribution of the gauges, how that's done, you can compensate a lot of this right at the measurement point. Okay, thanks.
Great question though, thank you.
Calvin, you had a comment?
Well, it was, gosh, yeah, I did. I think it was Pablo that mentioned about getting the rig to have a consistent way of understanding what breakover is and just doing that procedure. I suppose automation is going to get rid of that, but I'm hearing a lot of reasons why automation should be there for standardization. It was really my comment. I had personal experience trying to get the rig to, they didn't have a procedure. This is 4 or 5 years ago on it. They didn't even know you really needed to have a constant procedure. So I'm all for standardization there because it's a dead quality. I had a question with respect, Isabel, but did you assume obviously the hole diameter is constant? Would there be any implications for washout zones or overgauge hole sections for some of this work?
In terms of like lateral vibration, or where are we going?
Just in general, the results. I mean, I guess from a modeling perspective, is probably what I'm thinking of, is if there was an implication there, what normal would be. You make some assumptions on the whole geometry.
Yeah, and so it's sometimes when it comes to hole geometry and lateral vibration, it's like which came first, the chicken or the egg, right? You've got an overgauge hole, so your tendency to whirl increases, but then if you're whirling, then you're going to create an oversized hole. And so in this case specifically for this work, we didn't look at the caliper logs. Unfortunately, just being the service company, I don't have access to this data. But I'm not quite sure if Pablo's still on the call, because I know you guys were doing work with 3D calipers and looking at this vibration data. But unfortunately, from my end, we don't get fed that information. But there definitely 100% is a relationship between those things, and it does affect the dysfunction that we see. This formation itself and its desire to wash out. Pablo, do you have any comments there?
Yeah, it's different if you run a motor or an out of track RSS or the orbit. The profile it's not easy to quantify, but yeah, it's a good point.
If anyone wants to do a study with overgauge holes and give me some caliper data and run some sensors, I'd be happy to look at that data.
Okay, very good.
Yeah, we just don't want to cross that up into, just how hard it has been to do all these studies, right? I mean, it's been really hard to get the right data, and sometimes they don't match, and behavior, the patterns, the wear patterns are different depending on the type of BHA that you have, even with the same RSS. So I think this is just the beginning. There are a lot of things we got to understand a little better, but I think we nailed down the basics on downhole vibration that we wanted to get rid of or making it quieter. So it's a good point, though.
I think to just back on what John said before and his questions about how pressure would affect strain and interpreting this data, like I said, there was another service company who had a sensor in the hull. And when they saw that shift in downhole weight, I'm not quite sure how they're zeroing their downhole weight on bit, but I think it might be an automated process that literally just matched the two lines up and re-zeroed it and said that that weight, that increase in downhole weight didn't happen. So back to that idea of really understanding your data, really interpreting your data correctly, and spending the time to actually, instead of just saying, hey, that looks weird, maybe the sensor's broken, to spend the time and work out what's going on and understanding what's really happening.
Yeah, very good. Any other questions from anybody, guys? We still have a few minutes. We're not out of time, but
I came late. I was just curious, where is the location of this work listed in the paper where this was done?
I don't think it is. I don't know, Pablo, is that something we're discussing? I think everyone knows where it is, but I'll leave that to the
yeah, so as I said, the work that Isabel presented was focused in the Oklahoma Marietta Basin. But he only covers up to Q1 of 2022. We got another 15 months of work that covered the rest of the Oklahoma basins, Southeast Oklahoma and East Texas. And that's the one that is going to be presented in October.
Thank you.
all right. So Isabel, thank you. Pablo, thank you very much. Very interesting presentation. A lot of food for thought. Let's go back to the last couple of slides from the DSATS update, and then everybody gets to go back to their day jobs. Let me share my screen again.
Thanks, Demetrios.
Thank you, very good. So that brings us to the conclusion of the call. Those are the same two slides really that I have been using. About what we're trying to do in DSATS, to remind everybody the objectives, the goals, and invite participation. Really, knowledge sharing is one of the main objectives for a technical section, and like today, this was an excellent example of lessons learned and shared across company barriers. So I'd like to invite others, if you have similar studies or data or technologies that you would like to share with the industry. This is a platform here. These calls and these ads and the webinars are a platform to promote this knowledge sharing. So this is an open standing invitation for people to participate and share. The next community call will be 2 months from now, the second Thursday of September. It happens to be September 8th at 8:30 a.m. An invitation will be sent right before that, a week before that. I'll try to have someone else like Isabel today to come in and present, give us a technical update. I think these are extremely valuable for the community, this kind of talks. So with that said, I think we can stop here. If there is any comment or any suggestion, there is a point that John DeWard mentioned. I'd like to bring it up. So I know that the ATC concept reception hasn't happened yet, but we need to start thinking ahead for the next event, which is the drilling conference next March. And we're going to have the symposium there, the annual symposium, and the proposal is to bring in people from outside the industry, Tesla or SpaceX or NASA or something, to tell us a little bit more about how they dealt with these integration issues, interoperability issues, automation, putting the data in the right context, the same topics that we are discussing. So how does that sound? Does that sound like an interesting idea? This is a format that we have used in the past, 2016, I think, and it worked well. So I'd like to invite in feedback from the community, if that sounds of interest, if that would be a good format for that event. Feel free to come back with your opinions, here in the call or by email later separately or whatever. I thought it's good to have it there. So we have, you know, community feedback to give back basically what the community needs, you know. With that said, I think that we can close the call here. Thank you very much for coming in the middle of the summer, in the middle of the heat. I look forward to having you again in September. Thank you.
Thanks, Demetrios.
Thank you.
Thanks, Demetrios.
Bye.